In this section, we're going to introduce a special graph called tree. In 1857, Arthur Cayley studied hydrocarbons, in particular saturated hydrocarbons, which have K carbon atoms and 2 times K plus 1 hydrogen atoms. If the structure had, for example, 5 carbon atoms, then it would also have 2 times 5 plus 1, so that's 2 times 6, 12 hydrogen atoms. And it obeyed the following properties. Each hydrogen atom was bonded with one other atom. Each carbon atom was bonded with 4 other atoms. The diagram of the structure looked like this. This is an example of a hydrocarbon that has 2 carbon atoms and 6 hydrogen atoms. Notice that each carbon atom is bonded with 4, and each hydrogen atom is bonded with only 1. Through mathematical analysis of these graphs, Cayley predicted the existence of new saturated hydrocarbons, and later experiments proved his predictions were correct. This special type of graph is called tree. Here's another example. In planning a telephone network for an undeveloped area, the goal is to link together 4 isolated towns, and this is what we want. Each town must communicate with each other. That means the graph, the diagram, will be a graph, and the graph will be connected. And the other property is that it's not necessary that there is a direct link or a direct line between 2 vertices, between 2 towns. And here's a question: how to find a set of edges that will give a path between any 2 vertices and it has no more edges than necessary. And it turns out that there is a special type of graph that will satisfy these conditions, and that is called a tree. So here's the representation of a diagram that represents this problem, the 4 towns. And we begin by joining a line between any 2 vertices. So we have here a complete graph with 4 vertices. Starting from a complete graph, we can then delete the edges that are not necessary and still keep the connectivity. And also, there's no need to have a direct link or line between 2 edges, between 2 vertices. So here we can have 3 possibilities. So if we delete that edge, that, and that, notice that the 4 towns are still connected, and this is the minimum number of edges. If we delete one more edge, then we're going to lose connectivity. And then we can also have this example. See the same properties. All towns are connected, and there's no more edges than necessary. And here's the other example. Those 2 examples illustrate a special type of graph called tree. And here we define formally what a tree is. A tree is a connected graph that has no cycles. It's a very simple definition, and it has basically 2 simple properties in the definition. First, a tree is actually a graph. Now, the 2 properties are that this graph has to be connected. In other words, you should be able to have a path between any 2 vertices in the graph. And the other property is that this graph doesn't have any cycles. If you have a graph that is connected and has no cycles, then that's called a tree. And here we'll prove the first result of trees in our course. Theorem 5.1 that is stated in the book. It says that consider 2 vertices in the tree, vertex U and vertex V. The theorem says that there is exactly one simple path from U to V. Let's see how we prove that. Well, let's pick two vertices in the tree. And let's say that this vertex is U and that vertex is V. Now we have no idea how the shape of the tree is, but we simply pick a general vertex U and a general vertex V. Perhaps this vertex has an edge right there. Maybe it has another edge here, maybe a third edge, and perhaps there's only one edge. But at this point, it doesn't matter how many edges are connected to vertex U. We simply pick vertex U, and we know that there is a path from U all the way to V, because that's the definition of the tree. The tree is a connected graph. That means there is always a path between two vertices, because the graph is connected. Well, if there is a path from U to V, then perhaps the path will start here and it will go around and it will eventually will come and arrive at V. The theorem says that there is exactly one simple path. Well, let's suppose by contradiction that there is another one. If there is another path, if there is another simple path, then perhaps it will start here with U and then eventually will take a different route and it will arrive at also at V. If we have two different simple paths, then that creates a contradiction, because then we would have a cycle in this graph, and the tree cannot have any cycles. So that contradicts the fact that the tree has no cycles. So we cannot have another simple path from U to V. And it has to be simple, because if it's not a simple path, that means it has a cycle. A simple path is a path that has no cycle. So that proves the theorem. The next result, theorem 5.2, it says that in a tree with more than one vertex, there are at least two vertices of degree 1. Let's see how we prove that. Now, the idea of the proof of this theorem is based on the fact that there are finite number of vertices. So that means we can, if we're able to list all possible paths between any two vertices, then that's going to be a finite list. So let's say a tree has several vertices, maybe 1,000, 1,000,000 vertices. We don't know. So I'll just put a few vertices around here. And I won't draw any edges. I have no idea what the shape looks like. But because there are a finite number of vertices, then we can, between any two vertices, we only have one path. We cannot have more than one path. According to the previous theorem, there's only one simple path. So between this vertex right here and this vertex here, there is only one path. Between this vertex and this vertex, there is only one path. And pick any two vertices, there is only one path. So that means we are able to list all of them. It's a finite number. It's not an infinite number of paths. So we are able to list all of them. If we are able to list all of them, then there is one of those paths that it has the longest length. Perhaps it will be a path between this vertex and this vertex here. Let's say the path between this one and this one, let's say the length is 10, okay? And we say, well, that's the longest length in the, that's the path with the longest length. If that's not the longest length, then there may be another one, perhaps between, let's say V3 here and V7 here. Maybe the length, the path between V3 and V7, perhaps the length is 20. And maybe that's the longest. If that's not the longest, then there may be another pair, or maybe another um, pair that has also V3, maybe V3, V5 has a path that is longer than the path between V3 and V7. Anyway, there is a path that has the longest length. Take that path that has the longest length. Let's call the VA and VB here. Let's say that VA and VB has a path, has the longest path. So we are associating each path with a pair of vertex. So if the path from VA to VB is the longest, then we can say that those two vertices, VA and VB, are the two vertices of degree 1. Why is that? And that's the final part of the theorem. Why these two vertices have degree 1. So our claim here is that this vertex has an edge here, is connected to an edge, and this vertex here is connected to an edge. And our claim is that there is not another edge here. Well, suppose there is another edge, and that will create a contradiction. Let's say that there is another edge here. If there is another edge, then that is connected to a vertex right there. Well, that contradicts the fact that VA-VB has the longest path. Then that means that VA-VB does not have the longest path. We're able to find a path that is longer than the longest path, which is a contradiction. And the same thing applies to VA. Let's say VA is not a vertex of degree 1, then that means there is another edge connected to VA. If that's the case, then again we contradict the fact that VA-VB has the longest path, because then we just found a path that is longer. It has one more edge, and so it's longer than the longest path. So that's a contradiction. That proves that VA here needs to be a vertex of degree 1, and VB also needs to be a vertex of degree 1. And notice that this is true only if you have a tree with more than one vertex. If you have a tree, in fact, you could have a tree with only one vertex. One vertex, let's say A, that is considered to be a tree. This is a tree. One vertex is considered to be a tree. Why it's a tree? Because it satisfies the definition. It's a connected graph. Yes. There's only one vertex. There's no cycle. Yes. There's no cycle there. There's not even an edge, but that means there's no cycle. Then it's a tree. So that proves the theorem that a tree with more than one vertex, in a tree with more than one vertex, there are at least two vertices of degree 1. Next result, theorem 5.3. A tree with n vertices has exactly n minus 1 edges. This is a very important result, and it allows us to actually have a better understanding of the shape of the tree. So if a tree has 10 vertices, then the tree will also have 9 edges, n minus 1. If a tree has 20 vertices, then the tree will have 19 edges. Let's see how we prove this theorem. To prove this theorem, we're going to use mathematical induction on the number of edges and vertices. Now, suppose we have a tree. We're going to begin the induction when n is 1. So for n equals 1, that means a tree with only one vertex. Then that's easy. A tree with one vertex would be like that. And we couldn't have an edge, because if we have an edge, then we would need another vertex. You can't have an edge without the edge being connected to two vertices. So we don't have an edge, and that's a tree. And the number of vertices is 1, and the number of edges should be 0, which is exactly what this is saying. If we have one vertex, we have 1 minus 1 edge, no edge. So that proves the theorem for n equals 1. Now we can assume true for n equals to k for some k. Okay, what does this mean? It means that let's say we have a tree with k vertices, okay? A tree with k vertices, and that tree has k minus 1 edges. So every time we have k vertices, we have k minus 1 edges. So for a particular k. Now we're going to prove, let's prove the theorem, let's prove the result that it's true for k plus 1, right? For n equals to k plus 1. Now, how do we do this? Well, let's pick a tree with k plus 1 vertices. Okay, consider a tree with k plus 1 vertices. And here is the tree. Now, the tree is actually not, I will not draw the edges, but so just assume that there are edges here. Assume that there are k plus 1 vertices, and I will not draw the edges to make this simple. All right, so you have k plus 1 vertices. Let's take one vertex that has degree 1. And this is possible because according to the previous theorem, one of these vertices, one of these k plus 1 vertices have degree 1. At least two of them have degree 1. But let's pick one that has degree 1. Let's say, for example, that this one here, this vertex V here, has degree 1. Okay, vertex V has degree 1. And why is this possible? Again, because of the previous theorem that says that any tree with more than two vertices, with two or more vertices, have two vertices of degree 1. Now what we're going to do, if this is a vertex with degree 1, it has an edge. It has an edge that is connected to another vertex. Okay, let's say here U. Now what we're going to do, we're going to remove this vertex. Let's remove it for now. Delete that vertex and delete this edge just for a moment. When we do that, what it's left is also a tree. And why it's a tree? Well, because when we had this edge and this vertex, the graph was a tree. Since we delete one vertex and one edge, we did not create any cycle, right? When you delete an edge, you're not creating any cycle. And also, the tree or the graph is still connected. We didn't destroy the connectivity because we only delete this last vertex here in this edge. So there's no paths that were disconnected, that were broken. So what it's left, it's a tree. Now, because it's a tree with k vertices. Remember, originally this entire thing had k plus 1 vertices. We delete one vertex and the edge here. What it's left is a tree with k vertices. According to the assumption here, the induction assumption, a tree with k vertices has k minus 1 edges. So what it's left here is a tree and has k vertices, and therefore it has k minus 1 edges. If it has k minus 1 edges, then let's go ahead and put this vertex back. So we're going to put this edge back and this vertex back. We deleted for a moment. Now we put them back here. Now what we have is a tree with k plus 1 vertices, and we had k minus 1 edges, and we added this edge here. That means now we have a tree with k edges. And that proves the theorem, because now we have a tree with k plus 1 vertices, and that proves according to the mathematical induction, this is true for any value of n integer. And that proves the theorem. The next result, theorem 5.4, has two parts. And part A says that when an edge is removed from a tree, we remove an edge and we leave all the vertices. When we do that, the resulting graph is not connected. And part B says that when an edge is added to a tree, we add an edge without adding any new vertices, the resulting graph has a cycle. Now, this is not difficult to prove, and let's take a look at part A. Now, when we remove an edge from a tree, leaving all the vertices, so we pick any edge of the tree and remove it, but leave the vertices there, then the resulting graph is not connected. And the reason that happens is because when you remove an edge, then you're violating theorem 5.3. 5.3 says that if you have any vertices, if a tree has any vertices, then the tree has exactly n minus 1 edges. If you remove an edge, then you're going to have something that has n vertices but has n minus 2 edges. Well, that violates theorem 5.3. What you have now is not a tree anymore because you violate that formula. Now, if you violate that formula, that means it's not a tree. If it's not a tree, something happened that violated the definition of a tree. If it's not a tree, then you have two possibilities. You either create a cycle, or you disconnected the graph. But when you remove an edge, you don't create any cycle. You're not adding any new edges. You're not creating any new paths. That means the tree still has no cycles, but because it's not a tree, then there must be something that happened to the connectivity of the tree, and that means the tree is not connected anymore. Let's take a look at part B. When an edge is added, let's see if you have all the vertices of the tree and a bunch of edges, and if you add an edge, just pick any two vertices and you put an extra edge between them. Then the resulting graph has a cycle. And why is that? Well, again, when you add an edge, you're violating theorem 5.3. You will have a tree with, you will have something with n vertices, but that has n edges because you're adding one edge. And that's not possible because then if it was a tree, then it would have n vertices and n minus 1 edges. So something happened and that violated the definition of a tree because it's not a tree anymore. If it's not a tree anymore, one of the two things happened. You either created a cycle or you disconnected the graph. But adding an edge to a tree, that doesn't disconnect the graph, right? You're not breaking any paths in the tree. Therefore, you must be creating a cycle, and that's exactly what happens. Now we have one more theorem, 5.5, and you will see the proof of this theorem in the textbook. But this theorem says that these 6 statements, they're all equivalent. In other words, let's take, for example, statement A and B. If a graph is a tree, a graph T, if T is a tree, then that means that the graph is connected and the number of vertices is 1 plus the number of edges. Kind of similar to theorem 5.3 that we saw before, that says that if we have n vertices, then there are n minus 1 edges. It looks confusing here because it has a 1 plus. But let's say, for example, the number of edges is 10, then the number of vertices will be 11, right? So you always have the number of edges is always 1 more than the number of edges. The number of vertices is always 1 more than the number of edges. So if you have a tree, if a graph is a tree, then you know for sure that it's connected and the number of vertices is 1 plus the number of edges. And vice versa, if you do have a graph, you're not sure if it's a tree. Okay, let's say if you have a graph that you know it's connected, but you also see that the number of vertices is 1 more than the number of edges, then you guarantee that that graph is a tree. So it's another way of actually defining a tree, if you will. If you have a graph that is connected and it obeys this formula, then you know for sure that it's a tree. Here's another way to describe a tree. If a graph is a tree, then the graph has no cycles, and again, the number of vertices is 1 plus the number of edges. And this is another way of describing a tree. If you have a graph that has no cycles, you know for sure that there are no cycles in the graph. And you observe that the number of vertices is 1 plus the number of edges, then you're guaranteed that that's a tree. So all these statements are equivalent, meaning that all of these can also be used to define a tree. For example, another way to describe trees is to say that there is exactly one simple path between each pair of vertices. If you see a graph that has this property where there is exactly one simple path between each pair of vertices, then you're guaranteed that that graph is a tree. Here's another thing you can also use to describe the tree. If the graph is connected, and if you notice that removing any edge results in a graph that is not connected, then you know it's a tree. And one way to say that is that a tree is a special graph that has the minimum number of edges that will keep the tree connected, that will keep the graph connected. And here's the final way to describe a tree. If you see a graph that has no cycles, and you notice that if you add any edge between two non-adjacent vertices, that will result in a graph with a cycle, then you know that that graph is a tree. So this is saying that if you have a minimum number of edges and if you try to add an edge, that will destroy the definition of a tree, right? It will create a cycle. So you're putting more edges than it's necessary to keep the tree or to keep the graph connected. So this is theorem 5.5. Now let's go back to the original example in this section and see why hydrocarbons of the type that we described at the beginning, why that is a tree. Um, so we know that atoms form a compound, so the graph is connected. So you can, a compound is a structure where you can go from any vertex, any atom to another atom. So there is a path. So they're all connected. Also, in the hydrocarbon structure, there are K carbon atoms and 2 times K plus 1 hydrogen atoms. Now let's take a look at that. That means if we have K atoms and 2 times K plus 1 atoms as well, so we add those two, carbon atoms and hydrogen atoms, together, if we add the two sets, then we will have 3K plus 2, right? K carbon atoms and 2 times K plus 1 hydrogen atoms. Together, we have a total of 3K plus 2 atoms. And that would be the total number of vertices in that structure. Now, let's take a look at the degrees of each type. Degree of carbon is 4. As we saw at the beginning, a carbon bonds with 4 atoms, and a hydrogen atom bonds with only 1. That means the degree of carbon is 4, the degree of hydrogen is 1. When we add all the degrees, then we'll have 6K plus 2. Why is that? That's because degree of carbon is 4, and we have K carbon atoms. So we add all the degrees of carbon atoms. We have 4 times K. Now let's add all the degrees of the hydrogen atoms. The degree is 1 for each hydrogen atom. So it's 1 times the number of hydrogen atoms. So the sum of all the degrees will give us 6K plus 2. And we saw a theorem before in chapter 4 that says that the number of edges is half of the sum of the degrees. So if this is the sum of the degree, we divide that by 2, we have 3K plus 1. And now the conclusion, notice that the number of edges is 3K plus 1, and the number of vertices is 3K plus 2. So you have the number of vertices is 1 more than the number of edges. So you know that this is a tree because it's connected, right? It's a compound. According to this part B here, the structure is a compound, so it's connected, and you notice that the number of vertices is 1 more than the number of edges. Therefore, the graph, the structure of a hydrocarbon is a tree.